So in previous classes we have learned about converting a finite automata to a regular expression using the Kleen's theorem, or it can be called as RIJK method. In this video we will be learning about converting the same thing, that is finite automata to the regular expression using the Ardens theorem. Okay, so for that we are considering some variables like p and q. Okay, so this p and q will be treated as some regular expression, and this regular expression will be formed from the input alphabets based on the example. So p and q will be considered to be as a regular expression, and from that regular expression you will be able to derive an expression that is of the form r is equal to q plus rp. Okay, if you are able to derive this expression r is equal to q plus rp in this form, if you are able to derive, means you can write the same expression like r is equal to qp star. So this is a theorem, that is Ardens theorem, in order to convert the finite automata to a regular expression. Okay, so you know that the transitions will be based on the transitions, you will be writing the regular expression, and if some regular expression p and q is taken, and you got the expression of this form r is equal to q plus rp, then it can be rewritten as r is equal to qp star. So how these regular expressions can be formed, that we can see with the help of an example. Okay, so if a question is asked like converting the finite automata to regular expression, using the Ardens theorem, then our task is to formulate the regular expression to this form, and from there converting the getting the final regular expression in this format, r is equal to qp star. So how this can be done, we can see with the help of this example. So given this automata having 3 states, and you need to convert this automata, you need to find the regular expression for this automata. So while applying this Ardens theorem, you need to make sure that the automata should have only a single initial state, and also it should not have any epsilon transitions in order to apply this Ardens theorem. So these two things you need to keep in mind to apply the Ardens theorem. Okay, so we can move to the example. So how you have to do is consider the state q1 first. Okay, consider the state q1, and you need to derive some equation for the state q1. In order to derive the equations for the state q1, you have to identify the in transitions. Okay, so this is the state, and this is the state, and in transitions, input transitions to the state you have to identify. So which all are the input transitions? This that is from q1 to q1 itself using the 0 input symbol, and q3 to q1 using another input symbol 0, and also this q1 state is considered to be as the start state. With this informations, you need to find the equation. Like you can write it like q1 is equal to first it is an initial state, isn't it? So if you can write it like epsilon plus, so since the state is an initial state, that's why I have included this epsilon. Okay, only for initial state we will be using this epsilon in epsilon element. Then first input, what is it? From q1 to q1 a transition is there using the input symbol 0, so you can write it like q1 0, plus another transition from q3 to q1, so you can write using the input symbol 0, so you can write it like q3 0. So you can name this equation to be as 1, and then second state also you can consider. the way in which we have written this first equation, same you have to do for the second state also to derive the second equation. So here the intransitions for Q2 state is from Q1 to Q2 using the input symbol 1. So how you can write Q1 1 plus then Q2 to Q2 also there is an input transition. So Q2 1 plus Q3, oh here one transition it is left out, from Q3 to Q2 you will be having a transition that is 1. Okay, so Q3 1 second. Similarly for Q3 also you can write in transitions, only you have to take the in transitions. So for in Q3 only a single in transition is there, from that is from Q2 using the input symbol 0. So name this as 3. Now you have to solve these equations. Okay, so here this Q3 can be, Q3 is equal to Q2 0. This can be applied on equation 2. So 3 in 2, substituting the third equation to the second equation, you will be getting what? Q2 is equal to Q1 1 plus Q2 1 plus, in place of Q3 you will be substituting the value, it is Q2 0 1. Okay, then solve, try to transform this equation to the format R is equal to Q plus RP. So here R is Q2. So the second R is Q2. So the second term you have to start with the same Q2 value. So you can rewrite it as Q1 1 plus Q2. Q2 can be considered as R. So take Q2 from these both terms outside, 1 plus 0 1. Okay, now by applying this theorem, it is of the form what? R is equal to Q. So Q1 will be Q plus R, Q2 is R, and P is 1 plus 0 1. Okay, now how you can transform this equation to R is equal to, so this can be transformed as R is equal to QP star. How you can transform? R is Q2, isn't it? Q2 is equal to, Q is what? Capital Q. Here it is Q1, isn't it? Q1 1 and P star is 1 plus 0 1. 1 plus 0 1. Star. Okay, so this will be one equation. I name it as 4. Okay. Now what you have to do, now you got the value for Q2, a single term you have got for Q2, and now again Q1 you need to find the value. So substitute the value of Q3 in Q1 also, that is obtain value Q3 in Q1. One second. Okay, so Q3 in Q1, how you can write? Q1 is equal to epsilon plus Q1 0 plus, so I will rub this diagram. Q1 0 plus, what is the value of Q3? that is Q2 0, Q2 0, and in place of this Q3 only you have placed as Q2 0, and the remaining, this 0 will be placed over here, plus epsilon. Now what is the value of Q2 that you have obtained here, isn't it? So epsilon plus Q1 0 plus Q1 1, 1 plus 0 1 the whole star, and this 0 0 you have to put over here, plus epsilon. Okay. Now what you have to do, you have to convert this form into R is equal to Q plus RP format. Okay, so how you can convert? So you will be, so this epsilon is not required, isn't it? This epsilon, it is repeated. Okay. Now how you will be able to solve it? Q1 here, Q1 will be considered to be as the R, and you have to make the Q1 as a common term for these two expressions. So you will be able to write it like epsilon plus Q1 in Q1 you can take it out, 0 plus 1, 1 plus 0 1 the whole star, 0 0. Okay. Now it is of the form what? Finally you got like this, which is of the form R is equal to Q plus R P. So this expression will be treated as P. And you have to write it in which format? R is equal to QP star. R is equal to QP star. So which means that R is equal to Q1 is equal to what is that Q? It is epsilon, and P star is 0 plus 1, 1 plus 0 1 star 0 0. Okay, epsilon concatenated with any regular expression can be written as 0 plus 1, 1 plus 0 1 star 0 0. So this is the final regular expression. Okay, and this is final only because the Q1 state is considered to be as the final state. So which one is the final state? For that state only you will be finding the final regular expression. Okay. So this so Ardens theorem is like you need to solve the equations, or first you need to find the equations for the given automata, and the automata should not have any epsilon transition and only a single state should have, and the final regular expression will be based on the final state of the automata. And in order to derive the regular expression, you need to convert the obtained expression to the form R is equal to Q plus RP format, and finally if the expression is of R is equal to Q plus RP, then you can derive the expression as R is equal to QP star. Okay, so in any way the final state or expression obtained from the final state will be considered to be as the required regular expression. So so you need to solve for the expressions that is based on the final state. Okay, thank you.